I will discuss about diode resistance, diffusion capacitance and transition capacitance in today's class. Before that, we should know what is resistance. Resistance, it is the obstruction offered by the material to the flow of current. Actually, it is defined as the ratio of voltage and current and is measured in ohms. Further, this resistance is divided into forward resistance and reverse resistance in the case of diodes. The forward resistance is further divided into static resistance and dynamic resistance. And we will see one by one now. What is static resistance? We will see now. Static resistance. Static resistance, it is the resistance offered by the diode to the flow of DC current when a DC voltage is applied across the diode. Diagrammatically it can be shown like this. This is the diode with anode and cathode. This is anode and this is cathode. Cathode denoted by capital K and anode is denoted by A. And this is connected across the battery. Since it is forward bias, this positive terminal is to be connected to the anode and the negative terminal is to be connected to cathode. So this is the voltage applied across the diode. This is the forward bias condition. So how the current will flow? The anode will have holes and the cathode will have majority carriers, electrons. Okay? The majority carriers, electrons will be attracted by the holes will be repelled by this positive polarity. So the holes will move like this. Let the current due to holes be IH and the electrons will be repelled by this negative charge, though they will cross the junction. Okay, so the electrons current will be IE. So this is the actual current. So the conventional current will move in this direction, that is IE dash. So the current in this circuit will move like this. That is, this is forward bias. You can write forward IF, which is equal to IE dash plus IH. This is the current measured in amperes, and V is the voltage across the diode. Okay, this is the forward static resistance due to DC voltage. You can write DC voltage like this, VDC, and this current forward current can be written as IDC. So VDC by IDC is nothing but the current, that is resistance due to direct voltage and direct current, that is RDC is equal to VDC by IDC, measured in ohms. Right. This is about static resistance. In case of dynamic resistance, what will happen? In the case of dynamic resistance also, the diode will be forward biased and it offers resistance to the flow of AC current here by applying AC voltage across the conductor, not conductor, across the diode. Across the diode, AC voltage is applied. Here AC voltage is applied, so its symbol will be like AC voltage, VAC, and the IAC will flow through the circuit. So in case of dynamic resistance, this is the circuit diagram. The diode is, for the diode, the applied voltage is AC voltage and the current through the circuit is AC current only. So the resistance due to AC voltage is RAC, which is equal to VAC by IAC. Okay? So dynamic resistance can be formed like this. RAC is equal to VAC by IAC. Units are same, ohms only. Next we will see about the diffusion capacitance. Diffusion capacitance. Capacitance that exist in forward bias junction is called diffusion capacitance. Denoted by C with suffix D. C suffix D. CD. So the diffusion capacitance is a capacitance that exists in forward biased junction is called diffusion capacitance. It is defined as rate of change of rate of change of injected charge with the applied voltage. Injected charge with the applied voltage. Okay. Diffusion capacitance is that exists in forward biased junction is called diffusion capacitance denoted by CD. It is defined as rate of change of injected charge with the applied voltage. Okay, let us consider the forward biased PN junction diode. Okay, this is the junction. To try to understand what is this injected charge and what is the junction and how the charges are created near the junction. Okay, in P-type we have majority carriers, holes. In P-type majority carriers are holes. Each ion will have a companion, a hole. Each ion will have a negative ion will have a companion. There is hole here, and each positive charge in P-type, will have a electron. So the electrons are majority carriers in N-type and holes are minority carriers. Very less will be the holes. Here in P-type, electrons will be minority carriers and holes will be majority carriers. So I will try to understand what is diffusion capacitor now. Due to high concentration of holes in P-type, what will happen? Due to diffusion, the holes will cross the junction since the holes concentration gradient is very less compared to the holes in P-type. So they will cross the junction. In the same way, the electrons have high concentration gradient. The electrons has high concentration gradient in N-type, and in P-type they are the minority carriers. So they have low concentration gradient. They move from N-type to P-type. At the junction they cross and they recombine. So when they recombine, they disappear. That means these ions will be uncovered. So these ions will be uncovered. These electrons will be disappeared from this layer of charge, positive charge, and holes are disappeared from the layer of negative charges. This is called as layer of negative charges, and this is layer of positive charges. This layer of negative charges and layer of positive charges will act as a capacitor, having the charges, that is negative charges, and another plate will have positive charges. Okay? So the capacitor will be holding charges here in the junction. The capacitor having the negative layer of charges and the positive layer of charges will be holding the charges. When voltage is applied across this, in forward bias only this diffusion of capacitance exists. Forward bias. Okay. Due to recombination, this layer of negative charges will be there near the junction, and layer of positive charges will be there on the right side of the junction. These two will act as a capacitor and hold these charges. Okay? And what about the capacitance? That capacitance is called as diffusion capacitance. So that is equal to, diffusion capacitance is equal to dq by dV. dq is nothing but the charge, this total charge, positive charge or negative charge. And dV, that is the change in voltage, applied voltage. Change in applied voltage. And the Q is the charge. This is minus Q and this is plus Q in the depletion region. This is the depletion region and this is the junction. And junction have a layer of negative charges and a layer of positive charges. CD is equal to dq by dV. Its small change in the charge will be depending on the small change in the input voltage. That is input voltage, small change in input voltage. So CD is equal to dq by dV. The CD is called as diffusion capacitance, and this dq by dV can be written as dq by di into di by dV. di by dV. This dq by di, this dq by di is replaced by tau. Tau is the mean lifetime. It is the mean lifetime. It is the mean lifetime of holes and electrons. Mean lifetime of holes and electrons. Tau divided by dq by dA. Then coming to di by dV, di by dV, it is reciprocal of resistance. Now already defined, resistance is nothing but resistance is equal to dV by di, or V by I already defined. You can be written as dV by di in measured in ohms. Resistance. Reciprocal is for resistance, opposite is conductance. So this is equal to G. This is equal to G. G means conductance. Reciprocal of resistance is conductance. You can find out this di by dV from the diode current equation. And then find out this CD. So CD is equal to tau into G. We'll find out this G now. That is di by dV from the current equation. Is dq by di, which is the mean lifetime of holes and electrons. So we'll find out di by dV from the current equation, diode current equation. Diode current equation. That is I is the diode current, which is equal to I naught, the saturation current, reverse saturation current, into E to the power V, the applied voltage, eta into Vt minus 1. Eta is the emission factor. It is 1 for germanium and 2 for silicon, and Vt is the temperature equivalent measured in volts. Let us find out dI by dV. Let us differentiate this with respect to, let us differentiate the above equation with respect to V. So dI by dV is equal to I0 into e power V by eta Vt, and differentiation of beta by eta Vt, that is equal to 1 by, that is d by dV of V by eta Vt, which is equal to I0 into e power V by eta Vt into 1 by eta Vt. So this above equation, that is I is equal to I0 into e power V by eta Vt minus 1 will be approximately equal to I0 into e power V by eta Vt. Because V by eta Vt is much greater than 1. E power V by eta Vt will be greater than 1. So 1 is ignored here. So I is equal to I0 and e power V by eta Vt. So finally, dI by dV is equal to 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 G, which is equal to I0 into e power V by eta Vt is nothing but I only. I only. So as I, this complete part is substituted as I. Okay, I0 e power V by eta Vt is equal to I only. I into I into 1 by eta Vt. I into 1 by eta Vt. So di by dV is equal to G, which is equal to I into 1 by eta Vt. I is the diode current, and eta is emission factor, and Vt already told you this temperature, voltage equal to temperature. So this equation CD, that is the diffusion capacitance, is equal to tau into G, which is equal to tau into eta Vt, tau into I by eta Vt. So CD is equal to tau into G, where G is equal to I into 1 by eta Vt, I have written as I by eta Vt, tau into I by eta Vt, that is CD. This capacitance measured in farads. Measured in farads. The next one, leftover topic is transition capacitance. Transition capacitance can also be called as space charge capacitance. transition capacitance denoted by D with the suffix T. T means transition. It can also be called as phase charge capacitance. So because phase charge will be available in the junction only. That too in the reverse bias. This one diffusion capacitance occur in forward bias condition, whereas the transition capacitance occurs in the reverse bias condition. So let us consider the diode now, PN junction diode. This is the junction, and these are the negative ions with the majority carriers poles. So each ion will have a hole. And minority carriers are electrons. And in the N-type region we have positive ions with electrons. Majority carriers are electrons. Each ion will have an electron. And minority carriers are holes. Now biasing is reverse bias. Reverse bias is this positive terminal of the diode is connected to negative terminal of the external source, voltage source, and the N-type is connected to positive terminal of the external source. The positive terminal of the diode is connected to this negative terminal of the diode is connected to positive terminal of the external source. That is V, let us say, input voltage. Okay, this negative terminal will attract the holes. Holes will move like this. So the ions will be uncovered by the charges. These ions are having the companions holes. Those holes will move away from the junction and move like this. When they move away from the junction, these are uncovered. In the same way, the electrons will move away from the junction and these are uncovered. And there will be minority current, okay, due to the minority carriers, that is minority carriers in P-type are holes, and in minority carriers in P-type are electrons, and in the N-type they are holes. So these holes are repelled by this positive charge, and here the electrons are repelled by this negative charge. They will cross the junction, there will be a magnetic current that will be very negligible. But the capacitance is due to this charge. The capacitance is due to the charge accumulated here because of this reverse bias. And it is reverse bias, the holes in the P-type will move away from the junction and the electrons will move away from the junction, from the N junction. From the N-type, the whole electrons will be moved away from the junction by uncovering the ions. When they are uncovered, only a layer of negative charge ions will be there at the left side of the junction, and on the right side a positive layer of positive charges will be there on the right side of the junction. So because of this, a capacitance will be developed across the junction. That capacitance is called as CT, which is equal to dQ by dV. So dQ is the increasing charge due to reverse voltage, and dV is the increase in voltage. Because of this, a transition capacitance occurs, which is equal to dQ by dV. Okay, and we know that the current is defined as the rate of flow of charge that is I is equal to dq by I is equal to rate of flow of charge dq by dt, which is equal to dq by dt into dv by dv we can write. Okay, so current is equal to dq by dt, so we can written as dv by dq, dq by dv, dq by dv, dq by dv, dv by dt, dv by dt is equal to ct into dv by dt. So ct is the transistor capacitance. So with this, all the three topics have been covered. Thank you.